Hello learner, welcome to Manifested e-learning platform. My name is James Kenyani. We are yet again going to start on a new topic written on the board, similarity and congruency. So before we start the lesson, the learner, before attending this topic, the learner should be familiar with length calculation of area and volume and other regular shape. It will be useful for him in this topic. Ratios, construction of triangles, and scale drawing will also be applicable in this topic. The objectives. By the end of the topic, the learner should be able to identify similar objects, construct similar figures, state and apply properties of enlargement to construct objects and images, apply enlargement in the Cartesian plane, state the relationship between linear, area, and volume scale factors, and lastly, apply the scale factors in real life. But in our first lesson, in this lesson, we shall deal with some figures. We shall deal with some figures like the squares, circles, and regular polygons. So in the lesson, we shall look at the properties of similar. So on this topic, we shall look at particular figures. That's why I mentioned circles, I mentioned squares, and regular polygons. So the objective would be as I've written, the objective will be to enable the learner to understand the similar properties of squares, circles, and regular polygons. But one is asking, there is this word similarity. Similarity. What is similar? Two figures are said to be similar if they have the same shape but not necessarily the same size. If you look at them, they look similar, but they don't need to be of the same size. So two figures, two geometric figures, so there is something that comes there. They don't need to have the same size. So you'll find most of the figures we deal with, like triangles. What brings up the shape in such figures? It is their angles. It is their angles. Like, for example, a square would have right angles at all the vertices. So for our case today, as I've said, we want to look at squares, circles, and regular polygons. So we have squares, circles, and regular polygons. So as the objective goes, we shall deal with squares, circles, and regular polygons. So we are going to start with squares, and at this stage, all of you know some of the properties of squares. So we shall start with the squares. So on the diagram, we have two squares. One is A, B, C, D. And so it's 6 centimeters. 6 centimeters. So the first one is a square of 6 centimeters, and the smaller one is a square of 4 centimeters. So to understand this well, we go to our guiding statement about similar figures. We say two geometric figures are similar if they have the same shape but not necessarily the same size. What gives a figure a shape? It is how it is carved. One of the things that will give it that shape is the angles involved. So if we look at our figure, two figures, at the vertices we get right angles. Here we have, this is a right angle, that is a right angle, this is a right angle, this is a right angle, this is a right angle. Similarly for the other two. We can also look at the diagonals. Yes, if we look at the diagonals, there is something we shall get. The diagonals intersect. The diagonals intersect at right angles. The diagonals intersect at right angles. So if you take a ratio of any corresponding side, like BC over SR should be equal to BA over SP. BA over SP. So we find BC is 6. So this is 6. SR 4 should be equal to 6 over 4, which gives 1.5, which means they are similar. So there is something we come to get. A square is similar to any other square. A square of 3 centimeters is similar to a square of 1,000 centimeters. So what we get there, that any square, a square would be similar to any other square. A square is similar to any other square, irrespective of the size. So a square is similar to any other square. We shall go to circles. We shall go to circles. We shall go to circles. So if you look on the board, we have two circles. I can call this circle A, and that is circle B. So as I said, our description for similarity still goes here. Two geometrical figures are said to be similar if they have the same shape, but not necessarily the same size. So we shall go to our two circles. We have the first circle. If you look, we can see the circular shape. So if we are to give a radius, you could say that is R, and this will have the small r. So if you look at it, from one center, we can draw very many circles. From one center, I can use this center to draw this circle. I can use the same center to draw a circle of size equal to that. I can use the same center to draw a circle equivalent even to the size of the earth. So what we saw in a square comes in squares comes also to circles. Any circle is similar to any other circle. Any circle will be similar to any other circle because of the shape. The shape is the same. They can be inscribed, they can be drawn from a similar center. They can be drawn from a similar center. They can be drawn from a similar center. So a circle is similar to any other circle, irrespective of the size. Even if you have a small circle of radius 4 centimeters, it will be equal to a circle. It will be similar to a circle of the size of the Earth, with a radius of even 6,000 kilometers. Lastly, we move to the polygons. Luckily enough, I have some of the polygons here. So this regular polygon is called a hexagon. A hexagon. And I said, what gives a figure, a geometrical figure, is its shape. Its shape is some of the angles. Any polygon, any hexagon, however big, it might be bigger than these, will still have the same properties. Will still have the same properties. This angle will remain 120, 120, 120, 120, 120, however big it would be. However big it would be. So, irrespective of the size, what we'll get from this. So, if I draw this one here, so that will be a completion of that hexagon. Hexagon. So this will come under regular polygons. Polygons. And as I have said, the shape of that polygon is given by the angles we get here. So we have an angle here, which will be 120, 120, 120, 120, 120, 120. So for any hexagon, so in this case we are using a hexagon. We've used an example of a hexagon. It will mean that I can even draw another smaller hexagon within that. But so long as those angles remain 120, it will retain that shape. It will retain that shape. So what I'm saying, even if you inscribe another one, a smaller one, those angles will still be what? 120 degrees. It will mean that the smaller and the bigger hexagon, you can call this one and this two. So you can say hexagon 1 is similar So hexagon 1 is similar to hexagon 2 because of an obvious reason. The angles, inner angles are the same, so the shape is retained. So any regular polygon is similar to any other polygon having same side, same number of sides, having same number of sides. So like this hexagon, it has 6. Whether the hexagon has a side as long as 3 kilometers, it will be similar to a hexagon having a side of 4 centimeters. So those are the properties we've got in a square, a circle, and polygons. A square is similar to any other square. A circle is similar to any other circle. A regular polygon is similar to any other regular polygons so long as they have the same number of sides irrespective of the size. So that basically brings the objective we had in that lesson about properties of squares, circles, and regular polygons in relation to the topic similarity and enlargement. So as we come to the end of the lesson, I'm going to give an assignment. So I write it and then read it. So the assignment is on the board and it reads, construct two regular hexagons, one of side 6 centimeters and another of side 4 centimeters, and show why they are similar. So for the assignment, you'll do that. And at this moment, I thank you for the audience, and let's meet in the next lesson. Thank you and bye-bye.